So in section 4.1, we're going to work on graphing exponential growth functions and also on calculating compound interest using exponential growth functions. Key vocabulary you're going to need to know is what is an exponential function, and an exponential function is a function in this form: y is equal to a times b to the x minus h power plus k. Now, this is an exponential function. We're going to work in 4.1 with exponential growth functions, which is this formula if b is greater than 1. In 4.2, we'll work with exponential decay functions, and that is when b is less than 1. So an exponential growth function, if I were to graph it, would look something like this. It starts flat, it ends essentially vertical, and it grows as you move from left to right. The growth factor in a form for compound interest would be my account balance would be equal to my principal times 1 plus my rate divided by the number of times per year I compound to the nt power. And in this case, when we talk about what is the growth factor is this item in here. It's 1 plus a calculation of interest rate. Okay, an asymptote is a new idea, the concept of a limit. An asymptote is a line that my graph will approach but never quite hit. So in the case of the base form of this growth function, y is equal to 0, meaning the x-axis is our asymptote. So in the case of this exponential function, our asymptote would be y is equal to k. Now, the type of problem that we might use this for would be a problem like this, calculating the interest we have in an account. If I put $2,200 in a bank account and I want to check, is it better to get more interest, 3% interest compounded quarterly, which would be less times per year? Which is better? More times per calculated more frequently, or getting a higher interest rate? And we can make that comparison by examining an exponential growth function. Okay, some background here on growth functions. This is the graph of f of x is equal to b to the x power, which would be the same as y is equal to b to the x power. And you can see when x is 0, b to the 0 power would be 1. And when x is 1, it would be b to the first power, so 1b, and then here we'd continue on. Okay, so this is what the graph looks like. It starts flat here for exponential growth, and as it grows, as x approaches infinity, it comes close to being vertical. So when you're thinking about a graph like that, I know over here it's horizontal and I know over here it's vertical. What matters is this curving area here that we're looking for. That's the detail we have to find when we're graphing. Okay, so if I wanted to graph this particular function, what's going to be easiest for me is I want to see what happens when I'm taking 3 to the negative 1 power, the 0 power, and the first power, because that's going to define that curve I was talking about. Remember, a negative power inverts the base of the power, so this would be 3 to the negative 1 power is 1/3. Anything to the 0 power is 1, and 3 to the first power is 3. So I'd be at 1/3 here, 1, 1, 2, 3 here, and I can tell that my graph comes in very flat, passes through these 3 points, and goes out very steep. Okay, so that's pretty straightforward. Negative 1, 0, and 1 are going to be very good inputs for you for graphing exponential growth and for exponential decay. So let's take a look at what happens when we have, in essence, what I have here is a negative leading coefficient, a coefficient of -1. I'm still going to go ahead and create an input-output table using -1, 0, and 1. But I do have to follow order of operations. So 2 to the negative 1 power is 1/2 times -1 is -1/2. 2 to the 0 power is 1 times -1 is -1. And 2 to the first power is 1 times negative 1 is negative 2. So the effect that this has is it flips everything over. So you see at negative 1 I'm at 1/2, at 0 I'm at negative 1, and negative 2. So what's happened is my graph with a negative leading coefficient is now below the x-axis. Okay, so it flipped it over. Very similar to what we saw happening with square root functions in the last chapter. Okay, going into a slightly more expanded version, talking about the leading coefficient a little more. You're going to find what's nice about this is I'm still going to use negative 1, 0, and 1. My inputs are pretty much the same. 4 to the negative 1 power is 1/4 times 2 is 1/2. 4 to the 0 power is 1 times 2 is 2. 4 to the first power is 4 times 2 is 8. So when I go ahead and graph this, I'll be at 1, 1/2, 0, 2, and 1, 8. So you see what's happened with a leading coefficient that's even a small number like 2 is that my graph becomes very, very steep very quickly. Okay, that's partly related to the leading coefficient, but it's also related to the size of the base of the power. Okay, so the 4 has more impact than the 2 does because the 4 is being squared or being taken to powers. Okay, and again, you should see some consistency here. I'm using negative 1, 0, and 1 as my inputs every time, pretty much. 4/3 to the negative 1 power is 3/4 times 3 is 9/4. To the 0 power is 1 times 3 is 3. And to the first power is 4/3 times 3 is 4. Okay, so at negative 1 I'm at 9/4. That's a little over, that's 2 1/4. And then 3, and then 4. So now you can see with my base being a fraction, it flattens out my curve quite a bit. Right? The last one was very steep with a base of 4. With a base that's just a little bit over 1, you see it flattens out quite a bit and it's not as steep. Okay, so now practice this on your own. Do problems 9, 11, and 13 and 14, the graphing problems, and then come back to the lecture to finish out. Okay, now we're finally here at our full version of the function. We have h and k again. H again represents a horizontal shift. K is a vertical shift. If you remember in the last chapter when we graphed square root and cube root functions, we would identify h and k. Then we would create an input-output table without h and k, graph it, and then shift it by h and k. We're going to do the same thing here. So I'm going to do an input-output table, but I'm going to be graphing y is equal to negative 3 times 2 to the x power. I can see that h is equal to negative 2, and k is equal to 0. Right? This is x minus negative 2. That becomes x plus 2. And there's nothing being added at the end, so k is 0. Now I'm going to ignore it. I'm going to use the negative 1 power, 0, and 1 first power. 2 to the negative 1 power is 1/2 times negative 3 is negative 3/2. 2 to the 0 power is 1 times negative 3 is negative 3. And 2 to the first power is 2 times negative 3 is negative 6. And I'm going to graph without h and k. 5, 6. So again, the negative leading coefficient inverted my graph. It looks like this. And now when I want to introduce h and k, h is going to shift everything to the left 2, and then there's no movement up and down. So I take this point, I move it to the left 2. I take this point, I move it to the left 2. I take this point, and I move it to the left 2. And this is my new graph. Okay, so very similar to what you did with square root and cube root functions. We'll do another example, and then you can practice on your own. Now in this particular case, I'm going to look at this. There's nothing being subtracted from x, so I know that h is equal to 0. And what's being added on at the end is 2, k is equal to 2. So now I'm going to do an input-output table with y is equal to 5 times 4 to the x power. I'm still using -1, 0, and 1. That makes it pretty consistent. 4 to the -1 power is 1/4 times 5 is 5/4. 4 to the 0 power is 1 times 5 is 5. And 4 to the first power is 4 times 5 is 20. Okay, so what I'm going to do is I'm going to do everything by 2's, because I know I'm at 120, that's up here. So 0, 2, 4, 5. And here I'd be at 1 1/4, so just a little over halfway there. Okay, so very steep graph. I'm going to bring it in here and head out there. And the effect of h and k is I'm going to shift everything up 2. No movement right or left, up 2. So I take each point and I move it up 1, 2, 1, 2, and 1, 2. And now you notice that my asymptote changed. Remember, the asymptote is related to k. So y is equal to k is my asymptote. And then, so in this case, y is equal to 2 would be the asymptote. Right, and that's just a line my graph won't cross. All right, so go ahead and practice on your own. Do problems 19 and 20. And then when you come back, we're going to do some application and finish out the lecture. Being interest or compounding anything, so this is what happens with exponential growth. We're going to look at an account balance would be equal to the principal, meaning the starting amount, times 1 plus the rate divided by the number of times you compound per year. So remember, the principal is P, the rate is R, and it has to be expressed as a decimal, and N is the number of times per year you compound the interest. A is the amount in the account after T years. So also, when you think back to our vocabulary, this item here, 1 plus R divided by N, this is what's called the growth factor. Okay, so this is the growth factor. Okay, so if I want to take this information, I deposit $1,500 in a bank account. So P is equal to 1,500. It pays 3% annual interest, so the rate is equal to 3%, but as a decimal, 0.03. Compounded yearly, so N times per year. If it's yearly, that's 1. And if I plug these all in, I'll know my account balance is equal to 1,500 times 1 plus my rate, 0.03, divided by 1 to the 1t power. So what happens when you compound annually is, you see, we just get the rate, the n ends up having no effect. So this will be 1,500, 1.03, that's my growth factor, to the t power. Okay, so now I can use this function to find the value of the account in any given year after my initial deposit. Okay, so this is the basic idea we're going to be working with. Here's a problem dealing with computer viruses. So I'm still going to use basically the same formula, P times 1 plus R over N to the NT power. Okay, this is an N, I swear. In 1996, there were 2,573 computer viruses and other incidents. During the next 7 years, the number of incidents increased by 92% each year. So my starting position, that's the principal, 2573, where we start at the beginning. 1 plus. My rate is 92%. That's 0.92 divided by the number of times per year we calculate, but it says it's each year, so it's once a year. So that'll become 0.92 to the t power. So if I simplify this, 2573 times 1.92 to the t power. Okay, write an exponential growth model. That's what I've done. Okay, and then how many incidents were there in 2003? Well, this is years since 1996. So 2003 would be 7 years since 1996. So I would plug in a 7 for t. It says here to graph the model, and I've gone ahead and done that. I'm just going to go ahead and pull up my graphing calculator. So here's the, right, 2573 times 1.92 to the x power. Now, I replaced a with y and t with x, but that'll work out. And when I go to 7, I can see that when x was 7, we were at 247,485. So in 2003, 247,285. Okay? Use the graph to estimate the year when there were about 125,000 computer security incidents. So you can see that's going to be before 2003, right? We had 2,500 here. We have 250,000 here. 125,000 is in between those two. So let's take a look and try to find out where does that happen. So I'm looking for 125,000. I'm a little past it. So it looks right about 6 years. So you see at 5.96 years, that's when I hit the 125,000, but they want an estimate. So 6 years since 1996, that was about 2002. Okay, so in this case, I'm using the graphing calculator to help me out. You go ahead and get a little practice here. Do problems 28 and 29. Come on back and we'll finish out this lecture. So here I have the original problem. I'm going to deposit $2,200 in a bank account. That's my principal. That's not going to change. Find the balance after 4 years for each of the situations described below. So each one of these is a little different. So my account balance will be 2,200, in this case, times 1 plus 3%, 0.03, compounded quarterly, that's 4 times a year, to the 4t power. Okay, so that's my particular, this particular function. Now if I go ahead and say I'm just going to find the balance after 1 year, because that's going to establish the trend in terms of what's best. Okay, so I'm going to pull out my calculator and I'm going to take 0.03 divided by 4, and then I'm going to add 1. I'm going to take that to the 4th power, and then I'm going to multiply it times 2,200, and I get 2266.75. I'm going to round up because we're talking about money. So it's 2266.75. That's how much money I have. So when I do my second scenario, I'm going to have my account balance will be equal to my principal times 1 plus my interest rate, 0.0225, divided by 12, because we're monthly, to the 12t power. And when I go ahead and pull out my calculator to do that, I'm going to do 0.0225 divided by 12 equals plus 1 equals. I take it to the 12th power equals, and then I multiply it times 2200. And what I get is 22.50 and basically 1 cent. So 2250.01. And in our last example, my account balance will equal my principal, 2200, times 1 plus 0.02 divided by 365 to the 365t power. When I do that in my calculator, I'm going to do 0.02 divided by 365 plus 1 to the 365th power times 2200. And I get 2244.44. So we deposited the same amount of money each time, and in each different scenario we lowered the interest rate but increased how frequently we compounded. Now, in general, the more frequently you compound creates an increase in the amount of value. Right? The account will be higher with the same interest rate and the same principal. Compounding more frequently will give you a larger account balance. However, you can see that when you're thinking about which has more impact, interest rate or compounding frequency, it's interest rate that matters the most. Okay, so that's working with exponential growth functions. In the next section, we'll work with exponential decay functions.